Okay, so last time we were here, we started looking at electrolysis, and we talked about how very different it is to galvanic cells. Remember we started talking about that? Mm-hmm. Can you give us one quick difference, Clay? Paul?
There's a source of direct voltage, so it switches the way the electrons flow.
Correct, okay. Whereas a galvanic cell does what? It's like a battery, so it actually produces the voltage. Okay. What's another difference that we can see on this diagram? Electrolysis, Yang? Well done. Major difference is that the cathode is negative and the anode is positive, whereas for galvanic cells it's the other way around. However, the similarity is that for the anode, it's always oxidation, no matter whether it's a galvanic cell or an electrolytic cell. Okay? Now this is on the sheet down at the bottom, but just to highlight that those are major differences. Okay. Another difference for how it operates, we can see that so you turn the thing on, alright, the source of direct voltage starts pumping electrons from this side to the other, to the cathode, from the anode to the cathode, which means that we end up with a very negative electrode and a very positive electrode, and what happens now is the things in the solution, okay, so this is an aqueous solution of copper chloride, the copper ions start migrating towards the negatively charged electrode, cathode, and we have a reduction. I said it's a reduction, so copper 2 plus gains 2 electrons to form copper, and that's laid down on the cathode, whereas on the anode it's oxidation, so the chloride, negatively charged chloride, goes there, it's attracted by the positively charged electrode. Can you see, Monica?
Yeah.
Do you want to move to the other side? And what happens? What happens if we oxidize Cl minus? We get Cl2, and that's how we see these bubbles of chlorine appearing. Okay, so just to bring you up to speed, that's electrolysis. Right, and we had a look at this sort of schematic that compares the two and that table as well. Okay, and you can see the sign of the electrode is different. That's a major difference between the two. And however, for both of them, excuse me, oxidation always for the anode, reduction always for the cathode. So the saying that I had was an oxidation. All right, and it's easy to remember that the anode is always oxidation for electrolysis. If you think about it, the negative ones are always attracted to the positive anode, and so that's, if it's a negative, that means it's got too many electrons, it's bound to be. It won't be reduced, unlikely, okay, it'll be oxidized. So you can actually, even if you forget the rules or whatever, you can think about it and it'll come back to you. It's logical, it's common sense. So then we moved on to, and I didn't quite get to this last time, we started looking at so this first example was of an aqueous solution, all right? That was copper chloride in aqueous solution. If we have molten salts, what do I mean by molten salt? Jeremy, what does that mean? So molten just means it's melted. All right, so if it's sodium chloride, we probably had to heat it to like thousands of degrees, maybe 2,000, just to get it to melt. So molten salts just means salts that have been melted. So we need extremely high temperatures. But what it means is it excludes what from that? What's excluded? If it's melted. So the previous one was copper chloride in aqueous solution. If it's molten, we're excluding the water. Okay? So the most important thing about the molten ones is no water. Okay? So basically what happens here is we have to use inert electrodes. By inert I mean, Yang, give me an example of a platinum, well done. Okay, or gold is another one. Or carbon, graphite is another one. So make sure you've got a couple up your sleeve. What happens is the same thing happens. We turn the thing on, voltage, all right, that becomes the, what's the negative again, guys? Remember?
The cathode
Negative's the,
in the electrode.
okay, so this becomes the cathode. All right, we know that because it attracts the positively charged sodium, which are reduced, aren't they? So cathode's always reduction, so sodium plus electron to give sodium. And this is the anode. And this time, the same thing happens. Chlorine minus is oxidized to Cl2 plus 2 electron. Does that make sense? Okay, so I'm just differentiating between aqueous and molten because you can electrolyze both. They both have their place. Anyone have any questions about that? See how we've had to have heat at the bottom here? Really, really important that we have heat. Now, can you see any difficulties? Can you foretell any difficulties with this electrolysis, Paul?
I was just going to say,
Yep.
Does the heat replace the direct voltage in the previous?
No, there's still direct voltage here.
Yeah.
So electrons are still being pumped around the circuit, but the heat is required to melt something like salt. Has very strong intermolecular forces. Okay, it's got a strong lattice structure, so it needs I think its melting point's like 2000 degrees. But you can see, one of the difficulties would be that you're getting molten sodium. What do you know about sodium? Where is it on the reactivity series? You guys know? I had one lying around. There it is. Sodium is like one of the most reactive metals, and it even just reacts with oxygen. It can burst into flame with oxygen. So that could be a problem. Okay, but anyway, that's just something to note on the side. All right. So anyone got any questions about that? Is that sort of clear? Clear? Is that clear?
Yeah.
Are you sure?
Yeah.
Okay. So there's a difference between doing an aqueous solution and electrolyzing a molten salt. Molten salt is actually easier because we know what happens. It's like there's only one positive and one negative ion, right? When it's aqueous, it actually gets a bit complicated, as we're about to see. So it's good that you came because I'm pointing these important things out to you.
What's the main difference? If molten salt, there's no water.
There's no water, so those ions that are making up that salt are the ones that form basically their elements. So sodium forms sodium, and chloride forms chlorine gas. So they form their elements in standard conditions. Make sense?
Yeah.
So now let's just go back to looking at electrolysis of aqueous solutions now. Okay, so this is different to what we're just looking at. So now we have water, so water present. But when water is present, it's not just the anion and the cation of the solute that can be oxidized or reduced. Sometimes the water itself becomes involved. That's complex. Okay, that makes it complex. So we need to just explore that a bit. During electrolysis of aqueous solutions, the electrode reactions that occur, and therefore the products formed, depend on three things, which we're going to look at in a bit of detail: the nature of the electrolyte, the concentration of the ions, and the nature of the electrodes. Okay, so the nature of the electrolyte. What's the electrolyte? The solution it's in, or
Yeah, CuCl.
that's right. So CuCl2, for example, the copper 2 chloride solution. Bless you. You didn't sneeze.
I don't know.
Yeah, so that's the electrolyte, and obviously the electrodes are the cathode and the anode. So we can vary many things. Let's have a look at the nature of the electrolyte first, okay? And if we were to compare the electrolysis of copper 2 chloride and copper 2 sulfate solutions, setting it up like on the previous page, I'll quickly just turn back to the previous page. That sort of setup, okay, where we've got inert electrodes. Both are using inert electrodes. What would happen was that there'd actually be something different between them. So the first one's copper 2 chloride, the second one's copper 2 sulfate. We observe in the first one with copper chloride that there's deposition of copper at the cathode and formation of chlorine at the anode. That's one we saw on the previous page. However, with the copper sulfate, it's a bit different. copper deposits on the cathode, so that's the same. But look what happens at the anode. We get formation of oxygen. So that's different. Why? Why does that happen? What do you guys think? Any thoughts on why that might happen? Think about what's attracted to the anode in this case. Remember, the anode is negative. Is that right? I just lied to you. It's positive. Be awake for lies. Right, cathode is negative, anode is positive. Paul?
Because the O2 is more electronegative, so it's going to want to go to
Where's the O2 from, though?
the copper sulfate.
From the sulfate?
Yeah.
Okay, so not really. Okay. So sulfate does migrate to the anode, but it's actually the water that's oxidized. It's actually the water that's oxidized. Did you say that, Monica?
Yeah.
Yeah. So the reason why there's oxygen here is because sulfate is too stable to be oxidized, and I think if you've got your table of the electrochemical series, has anyone got their table here?
Yes.
Could you just see if sulfate's on there, please, Monica? Whereas water, so the equation for water, 2H2O gives oxygen plus 4H plus 4E minus, is included on there. Is sulfate on there? Yeah, that's sulfate, SO42 minus, is it on there?
Yeah.
What does it say?
SO42 minus plus 4H plus 2E.
But it's supposed to be an oxidation. So you see, it's probably not on there because it's not going to be oxidized. So we can actually just not write that, we'll just cancel it. So, whereas water, can you find the equation for water? It should be on there. What's its electrode potential? So that you've reversed it, right? Because remember, those are reduction potentials on there.
Well, no, because we know we start with OH minus. Can we start with that?
So water, so you need to have this exact equation. 2H2O gives oxygen plus 4H plus with 4 electrons. Is that on that table?
With 2H2O plus oxygen.
Gives oxygen towards oxygen.
Oh yeah, here it is.
At the bottom. So what is the electrode potential, what's the electromotive force, EMF, for this equation as it's written?
Negative 0.83.
But reverse.
Zero.
If it's reversed,
Zero.
it'll be a 0.8.
So it'll be positive if you reverse it.
Yeah.
So hang on, just to be clear, the way I've written, does it correlate with that?
Is it the opposite?
Yeah.
Or is it the other way around? Should it be positive or should it be negative? Do you want me to
It
check?
should be negative, I think. It's near the bottom.
Or maybe it's not even on here. Oh, there we are. It's up here. So it's actually going that way. It's negative 1.23. Oh, you guys you're caught on camera. That wasn't me. That was. So if you look on here, I'll just quickly show you. All right, if you look on this table, you'll see it over here. See water going to oxygen and H plus. That's positive 123, 1.23 if it's a reduction, but because it's an oxidation, it goes the other way, right? Okay, sulfate. Did you say sulfate wasn't on here?
Yeah.
Sulfate's on here, but it's a reduction. We want we need the oxidation, don't we? So yeah, it's way too stable. So basically, what happens is the water gets oxidized. Okay, the fact that it's a negative 1.23 is actually inconsequential because it's electrolysis. So you're driving non-spontaneous reactions forward. But the fact that it's even on that table means that it can happen. Okay, means that you can actually at least drive it. Does that sort of make sense?
Yeah.
Okay, so sulfate is too stable, but water can be oxidized. So water is oxidized to oxygen. So what would you observe with this kind of setup? Formation of oxygen in this case. So oxygen bubbles is what you'd observe, okay?
The bubbles at the anode.
Bubbles at the anode. And what else could you observe? How else could you test that this is what's indeed happening?
Would there be
Setting.
CO2 bubbles?
No, there wouldn't be. We're looking at the second one, copper sulfate one. So we've got a solution of copper sulfate with 2 inert electrodes. Paul?
Solid,
Yeah.
solid copper.
Yeah.
Solid copper would form on the cathode, correct? What's another observation? If you had some pH paper and you dipped it in, what would happen? Or some universal indicator. Look what's happening here. Yes, Jeremy.
It'll be acidic.
Well done. We're getting more acidic because we're producing that. So it gets more and more acidic. Well done. So it gets more acidic as well. Make sense? So it really matters. The electrolyte really matters in the case of electrolysis. Okay? You can't just put anything in it. It's not that predictable sometimes. Especially if you've got things like sulfates. Okay. Alright, so question for you guys. If we had sodium sulfate, can I turn to the next one? Alright, so over the page 3. Oh, it's actually just gone straight to the concentration. But I mean, we could think about electrolysis of, for example, sodium sulfate. Of sodium sulfate. What would happen? Any thoughts? Okay. Any thoughts what would happen here? So in solution we've got sodium plus, sulfate 2 minus, we've got water. We've also got H plus ions, OH minus ions.
It'll be the same as the last one.
Close. However, we need to just need to check that sodium compared with water.
Yeah.
What would happen over there? Okay. So what do you see in terms of sodium? Like, can sodium easily be made to sodium metal?
Not really.
No, compared to hydrogen it's actually worse. Hydrogen's 0, isn't it?
Yeah.
And what about sodium?
Sodium's negative 2.7.
Oh man, that's a big barrier to overcome. So the actual answer is, okay, at the anode, instead of sulfate, water, as we saw on the last thing, goes to oxygen. Okay, and instead of sodium, hydrogen forms hydrogen gas. So we form oxygen gas and hydrogen gas. So you guys need to really be on top of that, need to be on top of this stuff and be able to interpret that table in terms of
Negative 2.71.
so
How
for
do you know if it's too much? Because the last one it was negative as well.
yeah, but there was no way that sulfate was ever going to be oxidized. It wasn't even on the table. Okay.
But isn't it the same for this one?
No, what do you mean?
Oh, so the...
Yeah.
No, because you
sodium-
told me that sodium being reduced is like negative 2 point, what did you say it was?
2.71.
71, whereas hydrogen getting reduced
It's 0.
is 0. That's much more easy to do.
Yeah.
Okay.
So why do we use copper then? Like copper is...
This is sodium sulfate with inert electrodes.
Yeah, so that was negative.
That's inert electrodes. Sorry, Paul?
So
I'm still confused about
copper is,
something.
like positive 0.34. It's more likely to happen in the H.
But there's no copper in it.
But
This
in
is
the
sodium
last one.
sulfate. Oh, sorry, let's just go back.